All right, everyone, let's get the lecture going for this afternoon. Can everybody hear me okay at the back? You all can hear me okay? All right, yeah, I'll try and make sure I'm projecting there. You can all hear me okay. So today, we're going to be following on from some of those concepts that we saw last time. So last time we were thinking about, the energy involved in a single photon. So today we're going to be making that connection between the energy of photons and atomic energy levels, and also seeing some connections to nuclear physics. So those are going to be the big topics that we're going to be thinking about for the next couple of weeks until spring break. So let's take a look at a bit of the plan for today, some of the concepts that we're going to be learning about. Now, I always like to start with, some kind of picture that has some connection to what we're going to be thinking about. And what I like about this picture is that in one image, we've actually got connections to all the different concepts that we're going to be thinking about over the next couple of weeks. So probably the main thing you see here, this very beautiful image of a spiral galaxy. But the thing I'd like to draw your attention to over here is this supernova. A lot of the concepts that we're going to be learning about today and for the next couple of weeks, they all tie into lots of different things going on here. We can actually understand what's going on with the galaxy, how long the light took to reach us from the galaxy, by actually thinking about atomic energy levels. So you might think when we're thinking about atoms, well, we all know atoms, they're very small, galaxies very big. Something I love about astrophysics and cosmology is that we can make those connections between fantastically big and fantastically small scales. So by thinking about atomic energy levels, we can measure what's called the redshift to these galaxies, measure how much that light has got stretched out while it's traveling towards us. And then if we want to understand what's going on with that supernova explosion, we need to understand some of the nuclear equations that we're going to be learning about, because a type 1a supernova, it really is one of the biggest kinds of nuclear explosions in the universe. So we're going to be learning a bit about some of the physics that goes into that. Now, one of the main reasons that these particular kind of supernovae are so important for cosmology is because they explode with a consistent, standardizable brightness. And we can actually use that brightness to infer the distance to the galaxy that the supernova is sitting in. And in order to make that connection between how bright the supernova is and the distance, we need to understand this inverse square law over here. Now, when we're thinking about the inverse square law over the next couple of weeks, we're going to be thinking about it in terms of radiation and radioactivity, but it's exactly the same idea when we're thinking about the inverse square law for light. It allows us to relate how far away something is and how much light or how much radiation we're receiving from it. So those are all the different concepts we're going to be thinking about over the next couple of weeks, and they all tie into this one image here of the galaxy with the supernova. So we saw at the end of last lecture that we can have an individual photon and it's got that photon energy, E equals hf. So let's start the lecture today by thinking how we can develop that idea a bit more. So we've got this photon energy, E equals hf, but very often when we're thinking about photons, especially visible light photons, we like to think about the wavelength of the photon. So for this question here, we're just doing a little bit of algebra here. How can we get this equation for the energy of a photon from the frequency in terms of the wavelength of the photon? If you're not too sure about this one, we're just doing a bit of algebra there. So starting from E equals hf, and we know this relationship between frequency and wavelength and the speed of light. So that hint there, c equals f lambda. So we're just substituting what we get for that frequency from c equals f lambda into that equation for the photon energy. So give that algebra a go, see what you get. We'll take a look at the responses in just a moment. Okay, very good. So those responses coming in. Let's see what everybody thinks for this one. What's the energy in terms of the wavelength? Okay, so nobody going for D. Some people think it could be B or C. Now, what I'd suggest with this question if we start from this C equals F lambda, first step, solve this for the frequency. So we just get the frequency as C over lambda, and then substitute that into E equals HF. And then when we make that substitution, we get this option A over here. So very well done, everybody who gave this question a go, especially if you got that the energy is HC over lambda. So another very handy equation. Remember, there's no need to memorize any of these equations. If you know that E equals HF and C equals F lambda, you can put the pieces of the puzzle together, get energy is equal to HC over lambda. Now, one of the reasons why this is a useful equation is because whenever we're thinking about visible light, we almost always characterize the energy of those photons in terms of their wavelength. That's just the kind of natural way we think about visible light photons. And that kind of energy range is very useful when we're thinking about the energy levels involved in the structure of the atom. Now, how many of you have done a bit of atomic structure before? Okay, so maybe not necessarily in physics. Has anyone done atomic structure in chemistry? Okay. So we're actually going to be developing some of those ideas. Maybe you might have seen them in chemistry before or in physics. If you're seeing these ideas for the first time as well, that's absolutely fine. So the basic idea here, if we've got our diagram of an atom, so a very simple diagram of an atom, we've just got a hydrogen atom here. So we've got a little proton in the middle here. So if you've done anything about atomic structure before, we know that we've got the proton, we've got the electrons going around the protons, but the electron can't just go anywhere it likes around the proton. It can only go in specific energy levels about the proton. Who's done some of these energy levels, the electron energy levels? Maybe in chemistry might have done them before? Okay, great, a little bit, sure. So if you'd like to see where exactly these energy levels come from, that's what the challenge question tomorrow afternoon in the workshops is going to be all about. So maybe if you've seen these energy levels before, especially in chemistry, and you're curious to see exactly where they come from, we can now build on some of the ideas we've seen, a bit of the quantum physics, and we can actually calculate exactly where these energy levels come from. So if you're curious about that, definitely give the challenge question a go in the workshop tomorrow. But for today, we just need to think about this idea that electrons, they can only orbit this proton in specific energy levels. And if the electron wants to transition between different energy levels, it has to do that by releasing a photon with the right amount of energy. Okay, so if we're over here in this, n equals 6 energy level, and we want to drop down, let's go to n equals 3. So our electron is losing a certain amount of energy as it's changing there. Now we know that energy is always conserved, so if that electron has lost energy by dropping into that lower energy level, it's got to go somewhere, does that by releasing a photon with the correct wavelength. So in this diagram here, they've just indicated the wavelengths of the photons involved in all of those transitions. Now something that I think is amazing about this whole approach to atomic energy levels is that we can actually calculate exactly what all of these are from first principles. So I really do think it's an extraordinary way to kind of verify the physics is going on. But we can also measure these in a lab with a spectrograph. So has anybody tried any of these, these kind of, I don't know exactly what you call them, the like snazzy glasses, I guess. You know what I'm talking about? And you put them on and everything looks kind of rainbow colored. Has anybody tried these before? Okay, so if you haven't tried them before, come down after the lecture, give them a go, because what they do, so they take the light and they split the light into all its constituent parts. So if you just look at, a projector, you get the red, green, and blue colors. So these days you can't find so many like not incandescent, like neon lamps so often. But if you do see some neon lighting and you have some of these glasses, you put the glasses on and you can actually see all of the energy levels corresponding to the transition in neon. So it's quite good fun, okay? But even if you don't have any emission lamps around, they're quite good fun. You can see all the colors, everything's split into. So do come down, if you want to give these a try after the lecture. Or I'll bring them along to the workshop if you want to give them a go as well. So yeah, this is the idea that whatever the transition is between the energy levels, that's the energy carried out in the photon. So it also works the other way, right? If we come in and hit an electron in a lower energy level with just the right wavelength of photon, that's going to give the electron enough energy to move up into a higher energy level. Now, if we give the electron enough energy, sufficiently high energy, we can actually ionize the electron. Who studied ionization before? Has anyone done ionization? Okay, so what this means is that we give the electron enough energy that it's not bound to the nucleus anymore. So that's what we mean by ionizing something. So we need to come in and give the electron enough energy that it can just fly off, okay? And then it's no longer bound to the atom. So we're going to have some questions in the workshop where we think about the ionization energy involved in an atom and how much energy we need to come in with a photon in order to ionize that atom. So that's the basic idea with atomic energy levels and where that energy goes into photon wavelengths. Let's try an example over here. So you're still thinking about the hydrogen atom. So if you do have some hydrogen gas and you look at it through some of these spectral glasses like this, you see this really beautiful distribution of lines here, okay, including this nice big red line over here. So each of these colored lines are photons coming from specific transitions in the hydrogen atom, so transitions between specific energy levels. So what we can do is, by measuring the wavelengths of those lines, we can calculate what the energy difference is. So let's give this question a go. If we know what the wavelength of this light is, let's see what is the energy difference between those energy levels that these photons are coming from. So there's a couple of steps to this question because we're calculating the value of that energy difference in joules, because we've got Planck's constant there in joule seconds, and we need to convert that into electron volts, because that's a kind of natural unit when we're thinking about the energy involved in, photons or atomic energy transitions. So just take this question step by step. Step one, work out what that energy is in joules, and then step two, let's think about converting that to electron volts. And we got that conversion there, so 1 electron volt is 1.6 times 10 to the minus 19 joules. So take it step by step, see what you get for the energy in joules, and then step two, go about that energy conversion. All right, good to see those responses coming in. Let's see what everybody thinks for this one. What's the energy difference corresponding to this wavelength over here? Let's see. Okay, oh, this is interesting. Nobody's going for B or D. People mainly thinking it's C or A. Okay, so quite interesting here. So I guess step one, we want to work out what the energy is just in joules. So we've got Hc, then we divide by the lambda, that's 656 nanometers. So what do we get when we work that out? That's about, 3 times 10 to the minus 19 joules? Is that what people get? People get about 3 times 10 to the minus 19? Okay, so that's the energy in joules. So the next step, we need to convert to electron volts. So we've got 3 times 10 to the minus 19 joules, and 1 electron volt, it's 1.6. So we need, not quite 2 electron volts, basically. So correct answer is option A over here. So very well done, everybody who gave that question a go, especially if you got option A. People who got option C, did you get that it's 3 times 10 to the minus 19 joules? Did people get that? Okay, so if you did get that, I'm always getting the conversion between joules and electron volts back to front. So just kind of just check when you're working through that. We can definitely go through some questions like that at the workshop, because I find it very easy to just get that a bit back to front. So yeah, so that's the energy difference between those two energy levels in hydrogen. So even if you're still not super keen on electron volts, they are quite a handy unit of energy, because they're the kind of typical energies of visible light photons, and also they're typical kind of energy differences between energy levels in atoms. So they are quite kind of natural units of energy when we're thinking about the energies of photons and atoms. And even if you don't really like electron volts, I'd still much rather have, 1.9 of something than, what is that, 3 times 10 to the minus 19 of something. That's not nearly as intuitive. So yeah, that's the idea with that energy difference between those energy levels in the atoms there. So when we're thinking about the structure of atoms and electrons, and we're thinking about electrons moving between those energy levels there, they can only do that by releasing photons. But when we get a bit deeper into the atom and we get to the nucleus, we can have some more interesting things going on. So a nucleus can also release a photon, but that's going to be at a much higher energy level. We typically call them gamma rays. Has anybody heard of gamma rays before? Okay, so even higher energy than X-rays. But as well as emitting photons, we can get actual particles being emitted from an atomic nucleus. So let's think a little bit, got a few slides about the kind of physics that we can get going on in the atomic nucleus. So here we were just thinking about a hydrogen atom. We just got a proton in the center there. But of course, we can get much more complicated atomic nuclei with more protons, more neutrons. So let's take a look at what's going on here. Got a diagram here of an atomic nucleus. So we're indicating the protons in red and the neutrons in blue. Now, who's seen like, what do you call them? Like sort of labels for atomic notation for elements like this, if you've done chemistry, stuff like that. So we've got the atomic number and the mass number and the symbol for the element. Who's seen those before? I guess this is more of a chemistry thing, isn't it, right? Okay, so let's unpack what's going on here. So whenever we have an element in the periodic table, we've got a symbol for the element. So here it's just element X. So, symbols, I and what's that, Fe. I guess this is much more kind of chemistry thing. And then we have these two numbers to indicate what's going on with the nucleus there. So we've got the Z, okay, and that's called the atomic number. So the number of protons in the atomic nucleus. And the reason that that's the most important, the most fundamental number about the nucleus is because the number of protons is really the thing that defines what the atom is. So you can add and remove electrons from an atom, and then that might be ionized, but it's still the same atom. And again, you can add and remove neutrons from an atom, and you're going to get different isotopes. That's what we mean by different isotopes. But as long as you've got the same number of protons, then we say that's the same atom. And once you start changing the number of protons, then it's not the same atom anymore. So I like to think of that as the most fundamental number associated with an atom. So we've got Z, the atomic number. And then we've also got this other number, A, which is the mass number. So the total number of protons and neutrons. Now, something which I'd love to know the answer to. So you'd think, we've got atomic number, and that's Z, and then mass number, and then that's A. I honestly don't know why we don't have A for atomic number and M for mass number. I think that would make a lot more sense, and I don't know what the Z's going in there. And, you could easily confuse A for mass number with atomic number. That all just seems not quite as straightforward as it could be. But those are the conventions that we have. So we just kind of need to stick with them, okay, for Z for atomic number and A for mass number. So when we get interactions going on with the atomic nucleus, what's interesting about nuclear physics, and something that the chemists, they never get to play around with, is that we can actually change what the nucleus is from one kind of atom into the other. So if you're in the chemistry lab, you're really only dealing with the electrons and the physics of what's going on with those electron interactions. If you want to be doing all kinds of fun stuff with the nucleus, we need to be thinking more about nuclear physics here. So one of the things that can happen to our atomic nucleus is alpha decay. Does anybody know what is alpha particle? What's going on with alpha decay? Yeah, in the back. Yeah, absolutely right. Fantastic. Very good. So it's when this nucleus releases 2 protons and 2 neutrons. So shoots off, looks something like that. And that's what we call an alpha particle. So fantastic answer. Very well done with that. Okay. Does anybody know where else we might find an alpha particle? What else we might call an alpha particle? Yeah. Helium nucleus. Fantastic. Okay. So if we look at the alpha particle, so we've got 2 protons. Now, even if you're not much of a chemist like me, so we know, hydrogen, helium has got 2 protons, okay? So 2 protons and then we got some neutrons there. So it has to be a helium nucleus, otherwise known as an alpha particle. So if you hear someone talking about an alpha particle or a helium nucleus, they really mean the same thing. Well, actually, I guess an alpha particle, it's always got 2 protons and 2 neutrons, and I guess you can get different isotopes of helium. So yeah, alpha particle, that's always what we mean here. But you may see an alpha particle turning up as the nucleus of a helium atom. So that's what we call alpha decay, because we've released an alpha particle. So let's see, what is that going to do to our mass number and our atomic number? So if we have element X with mass number A and atomic number Z, what's going to happen to those numbers when we release an alpha particle? Let's take a look at what happens. So we've got our original particle. So we've released an alpha particle. Now, the alpha particle has an atomic number of 2 because it has 2 protons, and it has a mass number of 4 because there's 4 things in total there, 2 protons and 2 neutrons. So we've subtracted 2 protons and a total 4 from the mass number. So we've got to balance this in our equation. So if we originally had A and Z for our mass number and our atomic number, and we release 4 and 2, so our atomic number is going to decrease by 2, and our mass number is going to decrease by 4. So if we have a particle and it's released an alpha particle, if we have a nucleus release an alpha particle, we can see what it's going to turn into. So we need to look on our periodic table. We need to back up 2 steps on our periodic table. That's going to give us the element. And then we can see what isotope it is. So it's going to be whatever the original mass number was minus 4. So when we get alpha emission, it's quite exciting because we change our atom into a whole new kind of atom. Does anybody know what's some other kind of emission that we can get at the nuclear level? Any thoughts? Yeah. Yeah, exactly right. So the other 2 main kinds we can get beta emission and gamma emission. So let's take a look at what's going on with these. Okay, so we can get a beta decay. Now, a beta particle is otherwise known as an electron. So again, it's just an electron, but when it's being emitted, we tend to call them a beta minus particle. Okay, that's all we mean by a beta decay. So let's see what's this going to do to our mass number and atomic number, because it's a bit more interesting when we're thinking about emitting an electron. Let's see what goes on here. Okay, so we start with our original particle, same mass number and same atomic number. Okay, now we release our beta particle. Now an electron, the mass is really, really tiny compared to the mass of the proton or the mass of the neutron. So we effectively say that the mass number is 0. And the atomic number is really interesting because, so remember, the atomic number is the number of protons, and a proton has a positive charge. So if we're thinking about an electron, well, an electron has the same charge as a proton, but minus. So it effectively has an atomic number, even though it's not an atom, of -1. So kind of interesting. So what's really interesting is when we think about what this is going to do to our original nucleus. So we originally have a mass number of A. Now the mass number doesn't change, so our mass number is still A. But let's see what happens to our atomic number. Originally, atomic number of Z, and then we're kind of carrying away an atomic number of -1. So to conserve the picture, our atomic number goes into Z plus 1. So whatever element we were originally on the periodic table, if we emit a beta particle, we're going to move over to the next element on the periodic table. So kind of interesting. So like you said, of the kind of three main kinds of decay we might get is gamma decay. Okay, so gamma decay. Does anybody know fundamentally what's a gamma particle? So gamma particle is just a high energy photon. Okay, so even higher energy than an X-ray. So carrying that energy away over there. So let's see what that's going to do to our atomic equation here. So we start with the same mass number and atomic number. Now, a photon, it doesn't have any rest mass. It's not carrying away. It's not changing that mass number there. And a photon also doesn't have any charge. So it doesn't change the atomic number or the mass number of our original element. So whatever our element was originally, it can release a gamma particle. That's not going to change it into a different kind of element or a different kind of isotope. So those are the three main kinds of radioactive decay we can get and the effect that they have on their original, the original nucleus. Let's try an example where we're thinking about what's going on here. So suppose we've got some americium-241. So that decays by alpha emission. So we're releasing an alpha particle. Let's have a think. What's going to happen to our americium once we've emitted an alpha particle? Just remember the atomic number of this alpha particle, it's 2, and the mass number is 4. So we're going to be changing our americium by those values. So have a look which atomic number, which mass number corresponds by changing that americium-241 by those values. All right, very good to see those responses coming in. Let's see what everybody thinks for this one. What do we get here? Okay, no one going for C or D. Looks like most people going for option B. So if we start with the atomic number of 95, and then we take away 2, so that's going to have to be an atomic number of 93. So it's going to have to be one of these two. So I can see what everybody is thinking about. So to narrow it down, we need to look at the mass number. So the mass number of our alpha particle is 4. So the original mass number, we think about americium-241. 241 take away 4 is 237. So correct answer is option B. So very well done everybody with that question, especially if you got that, it's option B. So I think you guys get, that's the basic idea with alpha emission. Let's try one more example where we're thinking about beta emission, because that can be a bit more counterintuitive. So let's have a think about this one, see how this one works here. So we've got some carbon-14 up here, and our carbon-14 is decaying by beta emission. So let's have a think. What's our carbon-14 going to decay to when it releases this beta particle? This one is a bit trickier because even though the mass number of our beta particle is 0, the effective atomic number is -1. That makes it a bit more interesting when we're thinking about what's going to happen to our carbon once it's emitted this particle. So a bit more interesting. Have a think about what's going to happen. We'll take a look in just a moment. Okay, very good to see those responses coming in. Let's see what everybody thinks for this one. Okay, so now people thinking maybe C or D. Now I can kind of see what people might be thinking about with both of these, okay, because if we look at options C and D, they both have the same mass number, okay? So I think everybody's thinking along the right lines here because, you know, the mass number of our beta particle is 0, and we're starting with carbon-14, so we're not changing that mass number at all. So I think everybody's thinking along the right lines with this, and we can see that the atomic number, they've both changed by 1. So which is it out of C and D? Now, this is where it becomes a bit counterintuitive because that atomic number is -1. So what it does is it effectively adds an atomic number of 1 to the decay product. So we go from having carbon with an atomic number of 6, 6 add 1 takes us to an atomic number of 7. So correct answer is option D over here, okay? So very well done everybody who gave that question. The beta emission is a bit more a bit more tricky. Okay, so well done everybody with that question. So those are a couple of examples of what we can see with nuclear decay. Let's just think a little bit about how we measure, how we go about quantifying how much nuclear decay we get. Okay, so just got one slide here thinking a little bit about this idea of activity, or radioactivity. So we've got a picture over here of a Geiger counter. Has anybody seen a Geiger counter before? Okay, has anybody actually tried a Geiger counter before? Tried it? Oh, got quite a few. Okay. Oh, what kind of sources did you use for your Geiger counter? Okay, and just because of what the background was? Yeah. Okay. Did anybody try with like a particular source for your Geiger counter? Oh yeah? Oh wow, okay. Actually bring some americium in and you go and see the... Okay, and are the people just seeing the background with your Geiger counter, or? Okay, well that's great. I'm glad some of you guys have had a go with Geiger counters, right? Because it's I know it's quite fun. You can get an idea, and even if you don't have a particular radioactive source, you always get a few clicks, a few counts just from some background radiation there. Now, if you actually look closely at what the dial on the Geiger counter is, it's just counts per second. And it's logarithmic, so it goes, 1, 10, 100, 1,000 counts per second. So it just kind of goes click every time a radioactive particle goes in through this detector here. And it's really just those counts that we use to quantify how much activity we're dealing with. So it's just a measure of the number of counts per second. That's all it is. So I know when we're doing nuclear physics and everything, it can, well, I mean, it's not brain surgery, but it can seem kind of a bit kind of complicated, but we're just thinking about the number of counts per second. That's all there is to it, okay? And the number of counts, the activity that we get, we can describe it with this really simple relationship here. So that big old N, that's the number of radioactive particles that we have. And that lambda is the probability that each particle will decay in a given second. So got the number of atoms, and then that lambda, that's called the decay constant. So if you have a pretty stable atom, that decay constant is going to be low, it's not going to be decaying. If we've got something that's violently radioactive, that's going to be a lot higher. Okay, we're going to get some more activity. But it just tells us the probability for an individual atom to decay per second. Does anybody know the units that we use for activity? Any thoughts? Yeah? Okay. So sieverts, those are a unit that we use for kind of total received amount of radioactivity. If we're thinking about the units just in terms of the activity here, yeah? Bequerels, fantastic. That's great. Well done there. Well done. Okay. Yeah. So the units for this are Bequerels. And these are quite an interesting unit. They're not quite like any units we've seen before. So the units, they're Bequerels. And if we think, okay, so they're telling us how many counts we get per second. So in terms of our SI base units, the units are per second. So 1 becquerel is equal to 1 per second. But there's an interesting distinction between becquerels and the other units that we might be thinking about, which are units of 1 per hertz. So what else have we seen that has units of 1 per second? Any other thoughts? So if we just look at this, 1 per second, that's kind of the same units as hertz. Okay, so hertz measure of frequency, but there's a difference here. Okay, so they're not the same. So hertz are periodic. Okay, so if we say something has a frequency of 1 hertz, that means that there's 1 second between each event, and there's exactly 1 second between all the events. Whereas if we're thinking about becquerels, it's random. So it means on average, we're going to be getting 1 count per second, but that doesn't necessarily mean 1 count every second or 1 second between counts. It really just means in a minute we might expect to get 60 counts. That's the basic idea with how we go about quantifying activity and characterizing how radioactive a particular source is. Next time, we're going to think about some factors which influence the dose we receive. So if we're thinking about, sieverts, how much radiation we're actually receiving, how to deal with radiation safely. And the other big thing that we're going to be thinking about next time is radioactive decay. So if we know that we're getting a certain number of radioactive decays per second, we can calculate what's going to happen to our sample. So maybe we've got some americium there, that's going to eventually decay, due to the radioactivity. So just a reminder, so we've got the workshops tomorrow afternoon. Do give the challenge question a go if you're curious about where those atomic energy levels come from. It's also especially handy, get plenty of practice in for these, nuclear, decay questions, because they are pretty straightforward. You don't need particularly complicated calculations there. Just make sure you get the practice in, But for today, let's wrap things up for now. Oh yeah, if you do want to come and give the spectral glasses a go, do come down and give them a go. Otherwise, I hope everybody has a great afternoon, and I'll see you all in the workshops tomorrow.